Okay, so let us continue with support vector machines. We'll see a lot more examples now in this video. So in the previous video, we saw about the theory behind support vector machines and how to identify support vectors and how to set up the maximum margin decision boundary. Um, and then went through the spam email data set in detail, and depending support vectors, coming up with the normalized data set, and then going to the SVM math of forming the simultaneous equations involving the coefficients A1, A2, A3, A4, because we use 4 support vectors in this case. And then solving those equations using the online Gaussian elimination calculator. And once you get the coefficients, we can build the decision boundary, which is W times X, where W is the vector parameter vector theta1, theta2, and B, where B is the bias. In this example, the bias came out to be 0, so the decision boundary does go through the origin. And we found what is the margin of the decision boundary using the parameters theta1 and theta2. And then we validated the decision boundary actually for all the data points in the given data set. Remember, in the support vector machine modeling, we just consider the support vectors, which are the data points closer to the other class, as a basis to build the model. And so we're not really using the rest of the data points. So this will be actually a case of testing the data points. And then went through a couple of more test cases, basically data points that are not in the original data set. And then we also saw an important idea of how to get a decision boundary for the actual coordinate system, for the raw data coordinate system, using the result that we get from the normalized coordinate system, and how to use that decision boundary to actually classify the data points in the raw data set, as well as any new data point for that problem. So let us see a lot more examples in this video. So I really recommend looking at the previous video and then looking at this video. Okay, so the CRP temperature dataset is something you also analyze in the logistic regression module. Again, CRP is like what's called C-reactive protein that is synthesized in the blood. And its quantity is typically less, and it will be more if a person has infection. So when you have a virus infection or bacteria infection, the body temperature is also expected to high and get high, and CRP quantity in the blood is also expected to get high. So here we have a data set where we have the CRP quantity level measured in the blood in some unit, and then the temperature in Celsius for a person. So the class is so we want to basically differentiate or identify whether the infection is a virus infection or bacteria infection based on the CRP and temperature data. So we have 12 records here, 6 records for the virus and 6 for bacteria. Now, we are not really interested in one particular class of infection here. So when it comes to a data set like this, we could just arbitrarily assign one class as class 1 and the other class as -1. Remember, this is a support vector machine, which is primarily designed for binary classification. And the way the modeling is done is we assign one class as class 1 and the other class as -1. And either way is fine. Just pick one and just stay consistent with that. So the first step is to plot the raw data set, which is as it is, and try to visualize this. Now remember here, the CRP and temperature are not in the same level of magnitude. You can notice the mean of CRP is some 30 point something and the mean of temperature is 39 point something. There itself you can see a difference between the units, as well as a standard deviation, difference between the magnitude of the quantities, I would say, as well as the standard deviation is much different between the two. So the CRP has a lot of variation in the records in the data set, whereas temperature has relatively very less variation among the records in the data set. So this is again where that's why, if you use the approach that we are following for support vector machine modeling, that is identifying support vectors and coming up with the equation W equal to A1 S1 plus A2 S2 and so on. That approach will not work, especially if the data set has features that are not of the same magnitude. And also they have a lot of variation. The standard deviation between them among them is quite different. So if you're curious, you can take up the email data set if you want. And if you look at the feature values here for X1, X2, they are almost comparable magnitude. So instead of normalization, if you follow the same approach that we did with the normalized data set on the raw data set itself, you will be able to find the decision boundary that we have found ultimately here, X1 plus X2 equals 4. But if you follow the same approach for CRP temperature like data set, where the features are not of the same magnitude, then it won't work. So that's why we are transforming the raw data set to a normalized coordinate system and going through the process of building a SVM model. And then from the raw data, from the results that we get for the normalized coordinate system, we could build back the SVM for the raw data system. Like we did for the spam email data set, we can do for this CRP temperature data set as well. So, but again, as I said, the first step is to visualize the raw data. And you just plot it in Excel with the data set. And Excel is quite smart enough to pick up an appropriate scale for each of the font features here. And it will be able to make you visualize them in such a way that you can clearly identify the data points that are closer to the other class, even though they're of different magnitude. So let us do this thing in Excel. So this is my CRP temperature data set. Okay. All right. So the first step is to visualize it. And this is what we have here. So as I said, the CRP values range about from 5 to 65, or 3 to 65 actually, to look at the data. And the temperature ranges only from say 36 to some 43 or something. So not of the same magnitude and not of the same scale, standard deviation. But still, Excel can show you with just that scale that is needed, so that you can still be able to visualize the data the way we want to visualize. All right, so there are 12 data points in this or records, and the first step is to identify which one belongs to what category. Let me relabel the class 2 as -1. I was doing for some other classifier. So class 1 is still virus, the first 6 records, and then the next 6 records are for bacterial infection, which we call as class -1. So 4036, which is here, is the virus, and then 36.5 is again here, and then 21.4, 9.4, and then 11.1, this and so on. So basically, it looks like these 6 records over here, so that means lowest CRP values primarily look like targeting a virus infection, but not necessarily though. The top 2 record data points here, which are like what 17.3, which is the last one, And that really corresponds to a bacterial infection, as well as this one, 31.1, which is here, that also corresponds to a bacterial infection. But these four records are also for bacterial infection. So basically, we can say that so the reason why I'm going through the raw data visualization in detail is because that's a critical step for identifying the support vectors. So primarily these. Okay, so these 6 data points are for the virus class. This class 1. And the rest 6 are for the bacteria. So if you want to identify the support vectors, the closer data points in the virus class to the bacteria class are basically this one, which is 4036. Actually, we could, let me see. So this one, and then this one. So these two data points look closer to the bacteria data set. And so we could clearly find the two data points that are closer in to the bacteria data set. So that connecting them will get you a line connecting the support vectors in one class. And to find the data point that we can choose a support vector. So now we got 2. So we just need one, at least one from the other class. We could target one, but if you could find one more, that's good as well. So just go take this. So it's hitting this. So that could be one support vector. And we could extend this, but it's not really going through the other data points. So if you're not sure if it's a spam email data set, as long as we have 2 support vectors from one class and just one from the other class, we're good enough to proceed with the modeling. We don't really need more support vectors. Actually, the idea behind support vectors is to reduce the time complexity. Instead of considering all the data points, we just consider as many few data points as possible to build the model. But as I said, in order to set a direction for the maximum margin decision boundary, we need at least 2 data points from one class. Remember, we have only 2 classes here because it's designed for binary classification. So we have 2 classes and we need at least 2 support vectors from one class, and 2 is good enough. And once we get 2 support vectors from one class, from the other class, we just need 1 support vector. If we get 2 from there, that's good as well. Okay. So that's what I'm showing here in this slide, the visualization of the raw data set. So since we have, according to our convention, class 1 will be modeled as red data point. So we model the virus data points as red. And then the green data points are for the bacteria, and it's -1. And so we'll have S1 and S2 from the virus class as support vectors, and S3 is from the bacteria class. So then using the mean and standard deviation of CRP and temperature, so using the mean and standard deviation, we can transform the raw data set to normalize. So the way we do that is raw data, the feature value minus the mean of the feature value divided by standard deviation. We'll do that here. So it's just for visualization. Okay, it went off. That's okay. All right. So let us find the mean. So mean is found using the average function in Excel. So here it's going to be A2 to A13. Let me make it bigger. And this is, you can copy actually, which is average of B2 to B13. This is standard deviation, STDEV of B2 to B13. You can copy and paste it. So once you have this, so the records are not numbered in this version. It's numbered here though, but we don't need the numbering. So let us just copy the structure and let us get the normalized data set. So this is going to be A2 minus the mean of CRP is 30.2583 divided by 2.09646. That's the normalized value. And this is going to be B2 minus temperature, mean is 39.0333 divided by 1.0447. Now we can copy and paste this and for the other cells. So the mean and standard deviation. The standard normalized or standardized data either way is fine, is computed. So if you want to check whether the math that you did so far is correct, if you find the mean of the cells in each feature, we can use the same formula because the same range of cells. Same thing for standard deviation. Let's see. Oh, F2 to F13. Did I do some mistake? Oh, I'm sorry. The standard deviation I used A2 or B2, so it should be A2. See, that's why I told you. So the standard deviation of the normalized data for each feature should be actually 1 and the mean should be 0. We got the mean 0, but the standard deviation came out to be something different from 1. The reason is when I computed the standard deviation here, previously I was using B2 to B13, but I should have used A2 to A13. So I get the same standard deviation I got in the slide now. And here, because I copied and pasted, this should be from B2 to B13 here. I'm sorry. All right. So this is from A2 to A13, the standard deviation. This is B2 to B13, the standard deviation. So I should plug in the appropriate numbers. So let me put the whole thing. So it's good actually we checked it. So this is A2 minus the mean, which is 30.2583 divided by the standard deviation, 17.8059. This is B2 minus the mean. It's going to eventually come out to be something close to 0 for the temperature. The mean. Yeah, so let me check. This is not F2. Yes, but this is just for this record. So we have to copy and paste for all the records. Yeah. So the mean is something close to 0 and the standard deviation should be something close to 1. Okay, so make sure you type the mean and the standard deviation appropriately. So the B2 minus the mean at 9.033 divided by the standard deviation 2.09646. Okay, so we got the same data set like this one. So we have something to compare here. Okay. All right. So in the raw data set itself, we identify the support vectors. So the same thing can be retained here. So let us label the support vectors for our convenience. So we decided to use this guy, which is 4036 in the first virus class as support vector 1. And then this point is something should be 21.4, 39.4, which is this one as support vector 2. Is it the same ordering I'm following here? Yes. And then this, the last, using only 3, I believe. Yes. So this should not have been there. Let me change this. Yeah, this should have been this one. So previously I was modeling with 4, 2 from each, but then I want to illustrate the idea that we just need 2 and 1. So let me change this image. It is using this version. Okay, so our other support vector from the bacteria class is going to be the first data set record in the bacteria class. So let me go through that here. Is this one. It's 4237.6. I'm just confirming. So that's this first one. So that's S3. So those are the 3 support vectors that we're using here in the 2 classes. So once we get that, so using the support vectors, so we can, okay, we can visualize the normalized coordinate system. It should be the same as the raw data system, but we can check. I mean, the distribution of the data points should be relatively the same. So support vectors that we identified in the raw data system should be still good candidates as support vectors for the normalized coordinate system. Right. Okay. All right. So these 2 are support vectors, negative this 0.5471, this is our support vector, and okay, this is our other support vector. So we can circle this for reference if we want, or we can join them. Either way is fine. So these are 2 support vectors. So if you look at the relative distribution of the data points, they're more or less looking the same. That's what it should be. The normalization doesn't just change the relative distribution of the data points. It's just to bring the data points, the feature values in a comparable scale, we do normalization, but the power of normalization is such that the relative distribution of the data points won't change compared to the raw data. So we'll just go with just one data point, S3, as the support vector from the bacteria class, -1. So once we have this, we can start with SVM math. So I have written down here the 3 support vectors, S1, S2 from class 1, and S3 from class -1. So you can get that just from the Excel data. So you can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the data point. So we can just copy it, and this is the d Write down here like this, S1 equal to this, of course, with a 1 added as the dummy feature. And then S2 equals this. Sorry, S2 equals this. Make sure you write the correct support vector. So this is for class, these two are for class 1. This is S2. And then S3 is going to be this guy over here. So copy that, those two normalized values. So this is for class -1. So once we have this, the next step is to come up with the dot product table for involving the 3 support vectors. So here I'm typing things in such a way that this will be what you need to show as part of your solution for an exam question. So for S1, S2, so S1 to itself, so just square each entry 0.54. So known as I said, just use 4 decimal precision. That's good enough. And it's negative, but we don't need to consider that for squaring. So +1. So 3.3928. Then S1, S2. It's like product of positive, negative. So we have to be careful. 5471 times 0.4975. We can round to the 4 decimal precision. Put a minus sign before that, that's the value. Again, this is a negative and positive, so we can down to say minus 1.4469 times 0.1749, then 1 times 1 plus 1, so 0.4748. Now you can see there's symmetry here. S1 times S2 is same as S2 times S1. So immediately you can say S2, S1 is 0.4748 as well. Then S1, S3 is going to be 0.475471 times 0.6594. And then this is a minus and minus, so actually it will be plus. So 1.4469 times 0.6837. And then a plus 1 coming from that. So it's 2.35. So this is same as S3, S1 as well. So now you have to just do S2 times S2. So it's 0.4975 square plus 0.1749 square plus 1. So it's 1.2781. Then S2, S3 is going to be, this is minus plus, so 0.4975 times 0.6594. And again, this is minus plus, so minus 0.6837 times 0.1749 plus 1, so 5524. So 5524, same as S2, S3, 5524. Then S3 square, S3 times S3, so 0.6594 square plus 0.6837 square plus 1, so 1.9022. So this is our dot product table. So you can compare with what we have. Yeah, so that should be correct. Okay. So then, as I said, the equations that we need to have are 3 equations. And so let's write first W. So W is A1 X1 plus A2 X2 plus A3 X3. So W times S1, because S1 belongs to class 1, should be equal to 1. W times S2 should be equal to 1. W times S3 should be equal to -1. That means when W is multiplied by S1, which corresponds to this row, that should be equal to 1. So you can make use of that and say A1 times So you see this is S1 times S1, then S2 times S1, which is this, then S3 times S1, which is this. So you can simply say A1 times this 3.3928, which is S1 times S1. So 3.3928 plus A2 times, this is S2 times S1. So that should be this entry, 0.4748 plus, this should be this S1, S3. A3 times 2.35, this should be equal to 1. Then the second row, again, this is for 1. So A1 times 0.4748 plus A2 times 1.2781 plus A3 times 0.5524 equals 1. The third row should be now for -1 class. So A1 times 2.35 plus A2 times 0.5524 plus A3 times 1.9022 should be equal to -1. So these are three equations that we need to solve using, we can use Gaussian elimination, the online calculator, which is here. So if you have already used for a previous example, just click on the URL again, it should reload. So as I said, default, it will open up with 3 equations, and here we need only 3 equations. So we can just use what it shows up and just type those coefficients. So we need to determine A1, A2, A3. Here they call them as X1, X2, X3. That's fine. So 3.3928, make sure you type it correctly. 0.4748 and 2.35 equals 1. And 0.4748, 1.2781, 0.5524 equals 1 as well. And 2.35, 0.5524, 1.9022 is -1 here. So solve the system. As I said, you are more likely to get big numbers like this. I'll show you once again so you can copy and paste instead of trying to type in your calculator, because you could definitely avoid a mistake. So whatever it is, just Control V divided by this value. Control V again. So 5.4888 is your A1. And make sure you check the sign of what the values here. They're plus, and only X3, which is A3, is negative. So make sure you notice that, otherwise you may make a mistake for the rest of the calculations. Then A2, similarly, you can copy and paste. A3 you can copy and paste similarly to get the values. So I got A1, A2, A3 as 5.486 and this. So A3 is negative, remember. So this is our W vector. So now we can plug in the values of A1, A2, A3 as well as the support vectors and basically do the math to determine the 3 terms, which are theta1, theta2, and B. So again, for that, we need to do the pairwise multiplication and addition. So basically, it's plus here. But the sign of the coefficients A1, A2, A3 itself will tell you whether you have to eventually add or do subtraction. Okay, so I don't really put a plus there, but you can put it over here. So let me show you for this example one more time how to do this product thing, but it should be straightforward. So it's that 5.486 times this entry, which is, let's just use 4 decimal precision, 5471, then minus this 0.4975 times 2.174, then minus this 7.934 times 0.6594. So just taking that first term, multiplying with the coefficients, and it's negative 3.3118 something, so I call this negative 3.312. So sometimes I use 3 decimal or 4 decimal precision. Either way is fine, but I would recommend 4. Not going to change much your result. So now, for second term, we just multiply the coefficients with the second term in this vectors. So that's going to be 5.486 times 1.4469. So it's a negative sign. Make sure you include that. Plus 2.174 times 0.1749. Then it's negative and negative, so eventually it'll become positive, so don't need to worry about that. Plus 7.934 times 6.837. So that's going to be negative 2.133. Then for the constant, just 1 times this, plus 1 times this, plus 1 times minus this. So let's do that. For 5.486 times 1 does the same thing, plus 2.174 minus 7.934, we get negative 0.274. So here our B is not 0, unlike the spam email data set. So this is our weight vector. And the equation of the decision boundary is W times X equals 0. So this is a weight vector times x1, x2, 1. This is our standard data point in the normalized coordinate system, x1, x2, 1. So multiply each term. So negative 3.312 times x1 minus 2.133 times x2 minus 0.274 is W times X. So that's W times X. Remember, this is our decision boundary. So if you want to use this right away to validate the other data points, make sure you use the same sign that you have here. So this is what we determined as theta 1, theta 2, and B. And you have to use just those values, including the sign in your, when you just use W times X somewhere in your calculations. So remember, that's different from W times X equal to 0, because this is like an equation of a line. Whereas here, this is just the product W times X. And that's what we'll use to test any data point and find out whether it belongs to class 1 or negative 1. So let's go back to the Excel file and we can test it right away. So equals theta 1 times x1. So minus 3.312 times E2, which is that cell, minus 2.133 times F2 minus 2.74. So that's B times 1, right? So this is the equation that I just typed. So press enter. So we get 1 because that's what is expected, because we have used the data points as a support vector. So we should get W times X also as 1. And then for this one, it's 5.15. So 1 or anything greater than 1 is good. That's what we expect. And then 2 point something greater than 1 equal to 1. This should be 1 as well. This should be greater than 1. This is greater than 1 as well. So correctly I classified. Now this should be negative 1 and the rest should be less than negative 1. So yes. So we retain the same sign. So since everything is negative, we should not convert everything to positive. Don't do that mistake just for W times X. Just use them like as it is. The reason why I'm emphasizing that is, you now look at making this as an equation, W times X equal to 0. We can say this whole thing equals 0. So once you have it as an equation, let me do that. We can say this whole thing equals 0. Now for the math purposes, we can kind of divide everything by negative 1 on both sides and say this is like now all positive, plus 0.274 equals 0. So this is fine as long as you're working with W times X equals 0. But if you're working with this W times X, use the sign as it is that we got for W times X. Okay, so that's very important. I'm emphasizing that. Okay. So the next step, why we now deal with W times X equal to 0, is to visualize that decision boundary in our normalized coordinate system. So for that, we set W times X equal to 0, and we got this equation now. So what we need to do is get the 2 points that will connect. If you connect those 2 points in the normalized coordinate system, we get the equation W times X equal to 0. So for that, since we have a B term, we will just use x1 equal to 0 and try to see, no, and try to see what we get for x2, and same thing for the other variable. So x1 equals 0. So implies we get x2 equals minus 2 points, because if this goes to the other side, it's minus 2 points on 4 divided by 2.133. So I can write one intermediate step. This is 2.133 times x2 plus, so x2 plus 0.274 equals 0. So that means x2 equals negative 2.74 divided by 2.133, and that should get you x2 as this. Similarly, if you set x2 as 0, you can get x1 will be negative 2.74 divided by 3.312, that's this. So these are the two not data points, points. We can simply say that if you connect these 2 points, you get the decision boundary wx equals 0 in the normalized coordinate system. And let's do that here. So so we don't need this anymore. Let me type them. So 0, negative 0.12845, and this is negative 0.0827, 0. So this is our normalized coordinate system. Okay, so we got the two decision boundaries for the two classes. So if you highlight that, only up these 12 records are selected, just drag them down to choose these as well. So you got two new points added. So if you connect these 2 points and extend across each side, okay, so you get the decision boundary. It looks like it's close to the origin, but not really, because you have an intercept. Intercept means the bias term. So that's the decision boundary that we have for w times x equals 0. And we can get the margin of decision boundary using the coefficients theta 1 and theta 2. And since again we are going to square in that formula, I didn't include the negative sign. So it's going to be 2 divided by negative 3.312 square plus 2 negative 2.160 square, and some square root of that. So it's 0.5077. Now, as I said, you can cross check whether the math really makes some sense for the margin. So let's make it a little bit scale as 0.5. So the margin of the decision boundary really is what did we get? 0.5077. So this margin, so this is something like 0.3, negative 0.3, and it goes up to, yeah, so it goes up to 0.2. Yeah, so negative 0.3 to 0.2 is roughly 0.5. So negative 0.5 to 0.5 will be 1, but we are not covering this area and this area. So it's roughly half of it. So it's like 0.5. Okay, so just approximately, it need not be exactly the same, but just we can check. So once we have that, we are ready to, so we did already this evaluation of the rest of the data points in the normalized data set. So now we are ready to move on to the raw data set. So for that, what we'll do is we will use these 2 points in the normalized data set and get the corresponding raw points and connect them and get the equation w prime times x equal to 0 and so on. So let's do that. So for that, we'll just use this. Well, we can test as well if you want to before we do that. So let's pick up some raw data. X1 is 35, x2 equals 40. So we are testing the normalized system here. So we need to convert the raw data to the normalized version. So we'll use the mean and standard deviation. So for x1, 35 minus the mean of x1 divided by the standard deviation of x1. Again, the whole thing, 35 minus 30, the whole thing, and difference, then divide by the standard deviation. Similarly, for x2, the x2 raw value is 40 minus the mean, find the difference, divide the difference by the standard deviation. So the standard deviation, the normalized data is this for x1, x2, and then a 1 for the bias. So now to substitute, find w times x. Again, we are just finding w times x, not any equation. So we have to use the actual theta values that we got. So negative 3.312 times this normalized thing minus, because the theta 2 was also negative. Theta 1 times x1 plus theta 2 times x2 plus b, and b here is negative as well. So negative 2.133 times 0.4611. So just remember to use this. So again, I'm emphasizing because if you use w times this version, you'll get wrong, because here we have divided by -1 and change the sign. Then minus 0.274. So you get negative 2.1395, and that's less than 0. So it belongs to class -1. So if you plot that normalized data value here, it comes out to be somewhere over here. That's kind of away from the decision boundary w times x equals -1. So it goes even inside it. So inside means away from it. So that very well belongs to class -1. And here then I keep the x2 as it is, which is the temperature, and reduce the CRP. So if it is 35, that's more like, so -1 is again bacteria. So if you go to the raw data set and visualize what we saw, larger CRP values are more for bacteria. So 35 for 3240, I think is what we used. 3540. 3540, if you put it down here, 3540, it's somewhere here. Okay, so it makes sense, and we can check it when you go to the raw data set system as well. So we'll reduce the CRP from 35 to something like 20 and see what happens. So find the corresponding normalized version of x1. The x2 normalized version remains the same, and when we do the math, you get plus positive 0.6505. So again, this is what I said. We just compared the w times x with, is it less than 0 or greater than 0? Only for the what do you call if you don't have any outlier that lies within the margin in the given data set, you will expect the w times x value for all the data points to be either 1 or greater than 1 if it's class 1, and similarly -1 or less than -1 for class -1. If you don't have any outlier, means any data point within the margin in your classification. That means the SVM you're using is a hard margin SVM or a soft margin SVM. But if you look at this data point that we got here, its w times x came out to be 0.6505. And again, this was not part of our test data set. So in our normalized coordinate system that we used as the margin, we didn't have any outlier. So this is for testing purpose, I'm telling. So it's okay to get something to be like between 0 and 1. So we don't need to expect always the w times x value for the testing, for the test data point to be greater than or equal to 1. It could be greater than 0, but less than 1. That means it lies close to the decision boundary, but still it belongs to class 1, not class -1. Okay. And the farther away it is from 0 to class 1, the better. But still, once w times x is greater than 0, we just will classify the data point to belong to class 1. Okay, so that's something you should remember. Okay, so now let us convert this the normalized coordinate to the raw system. So for that, we need to use that formula, just the other version of this. So uh, we did that in the spam email case. Let me just copy the raw case. So if we have the normalized value, to get the corresponding raw value, what we need to do is use the normalized value times the standard deviation plus the mean. So in this case, if you're dealing with 0 for normalized, the product of standard with standard deviation is going to be 0. Just use a mean. So mean of x1, which is this, that itself will form part of the raw value. And then, so negative 0.12845 for x2. So times standard deviation of x2, which is 2.09 plus the mean of x2. So this is going to be your 38.76 for x2. Do the same math for x for the other point here. So in this case, the mean of x2 will serve as the value coordinate. Whereas for x1, you have to use this, which times its standard deviation 17.81 plus its mean 30.26, 28.78. So the two values we got are 30.26, 38.76, and then 28.78 and 39.03. So I did the equation thing previously for spam email. Let me do the same thing here one more time in detail. So if you have, let's consider XY coordinate system. And if you have 2 points, x1, y1, and x2, y2, then the equation of the line connecting the 2 points is going to be y minus y1 divided by y2 minus y1 equals x minus x1 divided by x2 minus x1. So here again, we are going to use, instead of x1, x2 system, xy system. So our x1, x2 values here will form x1, y1, x 30.26, 38.76. And this is going to be 28.78, 39.03. Okay. So once you have that clarification, this should be fine. So let me show the math here. So this is your y1, this is your y2. So y minus y1, which is 38.76, divided by y2 minus y1. We can do the math and actually put the number there. So y2 is 39.03 minus y1 38.76, 0.27. Whole thing is 0.27. Similarly, x minus x1, x1 is 30.26. You can do x2 minus x1, the math, which is 28.78 minus x1, so 30.26, so negative 1.48. So that's the equation basically, but we can simplify this. So the different ways we can simplify this. Let me see what approach I took here. Okay, I just used the raw divided by each term. Okay, so what we could do is just divide by the value in the denominator on each side. So 1 over 0.27 is going to be 3.704. Let's see, 37. So 3.7037 times y minus 38.76 equals negative 1.48. If you take the inverse of that, it's 0.6757. 3 or 4 decimal position is okay, and you can change between the two as well. So just you have to simplify this equation. So you can bring, let me do one step. So 3.7037 times y minus so 38.76 times 3.7037, 143.56 equals minus 6757 times x plus 0.6157 times 30.26, so it's 20.447. Since I use 2 decimals here, I can use 2 decimals here as well. 4.5 is good enough. So bring these two to this side. So this will become 0.6757 times x plus this 3.7037 times y. Then this is already a minus, and if this becomes to this left side, this becomes a minus as well. So it's going to be a minus 143.56. That's 20 point. So both add up, negative 164.01 equals 0. That's the equation of the decision boundary. Now we can replace x with x1 and y with y1. So x2. 3.7037 times x2 minus 164.01 equals 0. So this is our w prime times x equals 0. So what we can do is we can evaluate for any actual data point, this w prime times x. Let me do that here. So this should be x1 a2, that cell, plus x2, which is b2. Okay, so this comes out to be negative 3.648 thing, and I know a reason why it is. Let me check. It all become positive. So either way is fine. Um, mm, if I just switch. It's just the way you rewrite the equations. If you just bring these to this side, as long as you get one, this is just the opposite of what we were expecting. We were expecting this all should be greater than 1, and this all should be less than -1. But that because, remember, we are not doing this directly to get the w prime x in the raw coordinate system. We primarily did for the normalized coordinate system, and this is just an extension to show that we can get the equation for the raw coordinate system as well. So if you bring these to the other side, we get negative 6757 times x plus 20.45, then minus this thing 3.7037 times y plus 143.56. So that's equal to still 0. So minus 6757 times x minus 3.7037 plus 164.01 is still an equation for w prime times x. So we now plug in here the negative signs, you will get the sign we want. Okay. So if you're not getting the sign we're expecting, just do the other way, like I just did. Okay, and that's your decision boundary as well, equation, because once you have an equation, you can multiply by -1 on both sides and get the format we want. So it's still fine. It's still fine. So for our test point that we tried, the normalized coordinate system, which was like 3540, we can plug that here and see what we get for 3540. So you get -1, and that's what we found. Class -1. If you remember, for 3540, we said it belongs to class -1. So in the normalized coordinate system, we didn't have any confusion like what we just had, because we just used a theta x or wx as it is. That's why I again emphasize here as well, just use the sign that we find for theta in the normalized coordinate system. In the raw coordinate system, we didn't find the theta. We just went through an indirect approach. So that's why we have to play either way until we get the sign we want. But still, the coefficients are still has to be the same thing. It's just a sign, whether it has to be brought to one side or the other side. Okay. So either you bring the x term, this side, these two terms to the left, or bring these two terms to the right, will decide the sign of the equation. That's all it is. And we reduced this to 20 and it came positive, so that's fine as well. Okay. And here I just show a comparison with what we got for support vector machines. So for support vector machine, this is the equation we got. Sorry, for the logistic regression. For logistic regression, this is the equation we got for the same data set. And we got this 0.676 something, but we can kind of reduce this by, since the coefficient of x2 is -1 here, what we could do is divide this whole equation by -3.703, and that will make this to be -x2. So if you divide this value by -3.703, you'll get this -0.182. And if we divide this whole thing by -3.703, you get plus 44.29. And now these two equations will be almost the same. So this shows that the decision boundary that you find using either of the two classifiers are not going to be much different. They're going to be almost the same, if not slightly different. Okay. All right, so we'll take a break and then we'll go to the next data set. Okay, so let us continue. So in this example, we are going to look at a data set where as it is in the raw data set, we cannot find a linear decision boundary. Remember with SVM, so far we did with linear decision boundary, and that's what we did in logistic regression as well. And if in the case of logistic regression, for the same data set that we're looking at now, when we are not able to find a linear decision boundary, we kind of, not this one, it was a different data set, but let me pull it up. Okay, so it was this data set here, and we will handle this data set as well with SVM. But primarily, the idea is we have to transform or this data set to some other dimension. not dimension, to some other feature. Okay, so we cannot find a linear decision boundary in the raw data set as it is. So it's something like feature engineering. We either have to come up with a new feature or kind of play with the existing features and use some transformation of them. So let's deal one at a time. So we'll come back to this data set in the case of, what we did in logistic regression here is, so we know that x1, x2 by themselves do not form a linear decision boundary, but they form a non-linear decision boundary, which can be given by an equation x1 square plus x2 square equals some radius square. So we know that is kind of like a non-linear decision boundary. So what we could do is, instead of x1, x2, we found x1 square and x2 square. So the equation of a circle is x1 square plus x2 square equals radius square. So x1 square, we treat it as one feature. So it's one feature value plus another feature value equals some constant. So that's like a linear equation. So we fit x1 square plus x2 square as a linear equation. We found the decision boundary like this with logistic regression, and we're able to solve this problem. So that's one way. So we kind of added, instead of x1, x2, we used x1 square, x2 square as the feature, because we know that the decision boundary is non-linear and it's a circle. So we'll come back to this data set when we deal with that in support vector machine. But this is a one-dimensional data set here, where we are given the dosage levels of a medicine in some quantity, and if the level of the medicine is kind of low, the person is not getting cured. So that's our class of interest, because if you give a medicine to a person, we expect the person to get cured. That's normal. So if the person is still not cured, that's not normal. And as a convention we follow in this course, we'll target the not normal class as class 1. And that's what I have put here. And again, if the dosage is too high, the person's not getting cured. So that's not normal as well. So 1 is not cured, and -1 is the cured class. So that is as the normal, you know. If you give a medicine, we like expect the person to get cured. So if you give a moderate dosage of the medicine, then we see the person to get cured. That's again kind of as expected if you dig into a little bit more, because too much of anything is not good. So too much dosage of this medicine is not good. So some other problem comes up. Or if you give too low, it's not sufficient as well to cure the disease. So if you plot on the linear scale, so don't focus on the blue data points for now, just look at the green and red data points here on a linear scale for the dosage. So it's not possible anyway to come up with a linear decision boundary that clearly separates the two classes. So if I come up with something like here, these are the two data points that are close to each other, but whatever way we build the model, it's not going to be able to classify all the data points in the class 1 as class 1 and class -1 as class -1. No, because the boundary itself is not correct. Similarly, if you put the boundary here, that's not going to solve the problem as well. So clearly, as it is for the raw data, which is again in one dimension, there's no linear decision boundary that clearly separates the two classes. So we need to kind of add a new dimension and see if that can solve the problem. And that's kind of the idea behind what's called kernel trick. In kernel trick, we typically try to increase the number of dimensions as we're going to do this problem. And we could do it a little different as well. Again, the trick is what is main thing, you know, whatever the trick we use to basically transform the non-linear decision boundary, or to basically introduce a linear decision boundary among the features, and we know a method to solve with a linear decision boundary. So that's kind of what trick you employ to get there. And kernel is basically a terminology we use to refer to the transformation. So here we are going to add a new feature, and the transformation is to square the feature value. So we call it dosage square. And that's kind of one. So there are different ways we can do the transformation, and this is the squaring the feature values is one such idea, and that's called a kernel. Basically a function, kernel is like a function that takes a dosage, the feature, and gives you the square of that feature value. So that's kind of like a function that we call as a kernel. And the function here is to just square the feature value. So if you square the dosage and plot the dosage versus dosage square, and then this is a distribution you get in the raw coordinate system. It's still not clear how we could use a support vector machine. But what we could do is, if you normalize this dosage square data set, this is a raw data set. So you see the dosage like 1, 2, 3 up to 10, and square 1, 4, 9, 16, and so on. So find the mean and standard deviation of each of these features, dosage and dosage square. So the mean of 1 to 10 is 5.5. Mean of 1, 4, 9, 16 up to 100 is 38.5. And this is standard deviation for each of them. And the class assignment is as it is. The first 3 are 1, and the last 3 are 1, and the middle 4 are -1. And if you use the normalization approach, the raw data minus the mean divided by the standard deviation, you get the corresponding normalized data set. So now, if you visualize this, this is what we get. So kind of you have to zoom it if you do it in Excel. So this red data point is closer to this green data point, which what we saw in the raw data set as well, these dosage levels 3 and 4. And but remember, the x2 in the normalized scale is the normalized version of dosage square. Okay, so then the green data points. The green data points is 4 green data points, or the well, let me see. Dosage is the normalized version of x1. This is the normalized version of x1, and dosage square is normalized as x2. Okay, so that's important to realize. So x1 is the normalized version of dosage, and x2 is the normalized version of dosage square. So we're plotting here x1 and x2. Okay, so once we understand that, we are plotting the x1 dosage, x2 is normalized dosage version of dosage square. We get this distribution. So we look at this as some regular data set where we try to identify the data points that are closer to the other class. So the red data point, which is the class 1, is closer to this green data point, which is the class -1. And there are only 4 data points for class -1, and there are 6 data points for class 1. And this red data point in class 1 is also closer to this green data point in class -1, and vice versa. For this green data point, this is closer to the red class, and this is closer to the red class as well. So there's no it looks like there's no linear decision boundary because we have in between, but no. If you look at, if you zoom this, because the margin is going to be very small, so that's why I say you have to zoom this. That's why I didn't do this in Excel, but you can do this in Excel and see as well. There's nothing wrong in it, but it's the same process. Let me see if I have a copy of this. Okay, it's here. So if you zoom, if you plot this, This is what it is. And so this is dose x1 versus x2, the normalized scale for dosage and dosage square. All right. So these three are class 1, these three are class 1 as well, and the middle 4 are class -1. So, and the idea behind support vector machines is once you identify the closer data points, which are our support vectors, we need to connect the support vectors in the same class with a straight line. So we connect these two with a straight line. So these are two support vectors. And then we could try to draw a parallel line that connects the two green support vectors, which is this. So there is a linear decision boundary that separates the two classes. So if you zoom that here and see this. So you can come up with a linear decision boundary that will divide this margin. So everything above this margin, like here, above this decision boundary, will belong to the red data points, that's class 1. And everything below this decision boundary will belong to the green data points, which is class -1. So we do have a linear decision boundary if we do this kernel trick of doing a dosage square. Okay. So once we know that there's going to be linear decision boundary, we can go forward with support vector machine modeling. Because we have to first make sure that's like a hypothesis, do the visualization. That's why visualization is very important in data analytics when we use this machine learning models. Because we need to know the feasibility rather than just going to the math right away. So we'll call S1, S2 as the support vectors for the red class, and then S3, S4 as the support vectors for the green class. And these are the support vectors. This is the normalized x1, normalized x2, and then the 1. So class 1 for S1, S2, and class -1, S3, S4. Then get the dot product matrix, the dot product table. We know how to do that. And then we know how to write the 4 equations. So A1 times this plus A2 times this plus A3 times this plus A4 times this equals S1 belongs to class 1. So we say S1. Similarly, A1 times this plus A2 times this plus A3 times this plus A4 times this. S2 belongs to class 1 as well, so it's equal to 1. And this A1 times this plus A2 times this plus A3 times this plus A4 times this is -1 because S3 belongs to -1. And then the last equation. So solve these 4 equations using the Gaussian eliminator. We know how to do that. We get A1, A2, A3, A4, and then plug it in the weight vector. So this is a weight vector now. So do the term-wise multiplication and then addition, you get the weight vector, the parameters theta 1, theta 2, and b. Again, so using this, we can find the margin of the decision boundary, which is 2 divided by square root of 16.756 square plus 13.179 square root. So you can see is 0 less than 0.1. So that's why it's a bit difficult to visualize, but there is a decision boundary in which no data point falls. That's more important to realize as well. So there's no data point within that decision boundary. So it's clearly a hard margin SVM as well. So now you can find the WX value just based on this negative 16.756 and 17.1790, and then B. You can realize that, or you can see, let me show that here. So everything belonging to class 1, we get a positive greater than 1 W times, greater than equal to 1 W times X. For support vector S1, we get close to 1. And this S2, we get close to 1 as well. Then for class -1, we get negative values as expected. So S3, S4, we get something close to -1. And for the other 2 data points, we get less than -1. That's again as expected. But again, make sure you use whatever you get as the data values less and the bias as the values you enter to W times X. So now for the equation. So this is W times X. Now, if you want to equate it to 0 and find and fit plot, basically the decision boundary in the normalized coordinate system. Now we can make it equal to 0 and find an x1, x2. Again, since we have a bias, we can set x1 equal to 0 and solve for x2. We get x2 to be negative 0.1178. Similarly, set x2 equal to 0 and solve for x1, we get this. So then if you basically plot this in the normalized coordinate system, that's what I had here. It's going to, if you include this, we are going to get two new points added. And we just need to connect them and extend on both sides. You see here these two new points are in between the two lines. So it lies over the decision boundary. And that's actually the dividing line for the margin. So again, as the same trick, we can use these 2 points and convert to the raw case as well. But before that, let's do some testing. Let's say the dosage level is 3.5. You know, there's a transition at 3 and 4. At 3, the person is not getting cured. At 4, the person is getting cured. So let's see at 3.5 what the model is telling, whether the person is going to get cured or not. Okay. Before we do the normalization of the test data point, we need to add the new feature x2 because x1 is 3.5, but x2 is what? The dosage square. So the dosage square is 12 point square of the dosage 3.5, so that's 12.25. So these are our raw data x1, x2, and using their mean and standard deviation, we need to normalize them. And this is the normalized data point. Add a 1 or include a 1 as part of the bias. So we can now use the theta 1 times x1 plus theta 2 times x2 plus the bias. Remember, this is what we got at theta 1 w times x, theta 1 x1 plus theta 2 x2 plus bias. And we get it to be negative 0.1022 plus wx. And is it less than 0? So that means it belongs to the negative class negative 1. Now, you can also realize it's very close to 0. It's just less than 0. So we say it's negative class. So 3.5 is kind of like a cutoff. If you go above 3.5, you're more likely to see the person getting cured. So between 3 and 4. With just 3.5, the model is telling the person still not getting cured. So what about if you make it 7.5? Because again, between 7 and 8, there's a transition. At 7, the person's getting cured. At 8 is not getting cured. So let's try with 7.5. So again, 7.5 is the one-dimensional raw data. Sorry, this 7.5 is one-dimensional raw data. So we need to scale up as part of the kernel trick. So x1 is still 7.5, but x2 is going to be dosage square. So that's 56.25. So using the mean and standard deviation of x1, x2, the raw data, we need to normalize it. So this is a normalized version of the x1, x2. And now we plug it into the w times x, we get again negative 0.1222, which is negative. So again, 7.5 will belong to class negative 1 as well. So between 7 and 8, if you stay less than 7.5, the person is going to more likely to get cured, not 7.5 or above. So then again, the same idea of getting this into the actual coordinate system. So what you need to do is find the raw coordinates for this normalized coordinates. We know how to do that using the mean and standard deviation. And once you get those two coordinate points, we need to plug it in the equation for a line connecting 2 points and try to get the equation. So in this case, I'm getting the w prime times x as this. So that's your x1, x2 again. So what we could do is we could plug the raw data x1, x2, which is dosage and dosage square, into that w prime times x, and we see for w prime times x greater than or equal to 1, or greater than actually 0, greater than 0, because this is the equation w prime times x. So anything greater than 0 is class 1. and anything less than 0 is class -1. So we are not guaranteed to find things greater than or equal to 1, but as long as it's greater than 0, we can say that's class 1. So again, as things are, as long as things are less than 0 for w prime times x, that's class -1. So this is again greater than 0, so class 1. Okay, so if this is the equation for the decision boundary in the raw data scale, you do the kernel trick and see it as a two-dimensional system, x1, x2, the dosage and dosage square, and that's the decision boundary for the raw coordinate system, or the actual coordinate system. Again, we cannot say it's actual still because it's a transform. So the kernel trick does the transformation from one dimension to two dimension in this case. So we can say it's the actual transform coordinate system. So that's more precise. It's not just actual, it's actual transform coordinate system. Okay. Now, so another example. So this is a four-dimension system, a refractive index data set that we also did with logistic regression. So here we have four features, and E is a class actually. Now with the four-dimensional coordinate system, it's very difficult to visualize and identify the support vectors. So the only idea I could suggest with the techniques that we know so far is to see if any other classifier was used to model this data. And we did use logistic regression to model this data. Let me pull it up. So this is the logistic regression model. So we found the theta values using the online logistic regression calculator. And then we found the theta x. If you remember, I think I did it in Excel. Let me see if I can pull it up. Is model 4 or model? Should be here. Let me check if I have. But okay, it's here. So we did this with logistic regression, and yes. So this is our theta times x with logistic regression, and if you can check, cross-check the parameters. Yeah. So the theta 0 was 28.6166. And that's what we have here. And then negative 3.3306 for theta 1, and then to theta 4. So plug in this as theta times x, and again there with logistic regression, if theta x is less than 0, that's negative class, that's class 0, and if it's greater than 0, that's positive class, which is class 1. So again, the theta x magnitude kind of indicates how close is the data point to that linear decision boundary that separates the two classes. So the the largest of the negative numbers, because with the negative numbers, we say something is larger if that number along with the without the sign. So actually, among all these negative numbers, negative 16.39352 is the largest. Even though 16 point something is smaller compared to 20 point something, 26 point something, and 30 point something, and so on. When you consider along with a sign, negative 16.39352 is actually the largest of all these numbers. So the larger number for theta x indicates this data point is more closer to the decision boundary among the negative class 0 data points. Similarly, now for the positive cases though, the smaller the theta x value, the closer the data point is to decision boundary. So if you go back to logistic regression, that's what we saw with spam email, the two-dimensional data set. So let's check. This is a decision boundary for spam email data set. So these ones that are more closer to the decision boundary are going to have a smaller theta x value, and these ones that are further away from the decision boundary are going to have a very large theta x value. Likewise, the green data points, these are closer, so they're going to have, I mean, like negative 16, the larger theta x value because they're more closer. And if you go farther away from decision boundary, like negative 30 and so on, they're going to have a smaller theta x value, considering along with the sign. So using the theta x value, we can find out which data points in each class are more closer to the decision boundary. And from that perspective, this data point is closer to decision boundary in class 1, and this data point is closer to the decision boundary in class -1, which is class 0 in logistic regression. So we are going to use those two data points as a support vectors because they are closer to the decision boundary, so they are more closer to each other as well in the other class. So with that idea, we'll use this second data point as the support vector for class -1, and this as a support vector for class +1, and go through the math. Okay, and the rest is as usual. So that's the only where the number of dimensions will be a problem. But once you identify support vectors, we can go through the math as usual, find the mean and standard deviation of each of the features and use them to normalize the data set. And here, since we cannot visualize and we cannot clearly say about the other data points which are more closer to each other as well, because this is just with the hypothesis. We are telling that since these two are smaller in each, smaller and larger in their respective classes, we are telling they're closer to the decision boundary, so they should be more closer to each other as well. So let's go in this case with just one support vector from each class and see what happens. So again, since using just two data points as support vectors, building the model, the other data points can surely serve as test cases. So if the other data points get classified to the respective classes with the model we are going to build, that's an indication that with just two support vectors, we are able to manage here to build a more accurate model. So, excuse me. So with S1, S2, as a two support vectors, one for each class, we just need to build a small data dot product table, S1, S2. So take again, the dot product is still the same, just do the term-wise multiplication and add them. If you're doing S1 times S1, just square each term and add them up. So we get all these things. So since there are only two support vectors, there are only two equations to solve. So that's going to be A1 times this plus A2 times this. And this for S1, so it's class 1, 1. Then A1 times this plus A2 times this, and that's for S2, so it's class -1. And use the calculator online Gaussian elimination, we get A1, A2 to be this. And then W equals A1 S1 plus A2 S2, do the math, and this is what we get as theta 1, theta 2, theta 3, theta 4, and then the B. Since we have 4 features, we get 4 theta parameter values, and then the bias B. So using this, we can say what is W times X, which is this W times X, theta 1 X1 plus theta 2 X2 plus theta 3 X3 plus theta 4 X4 plus bias, and we accommodate the sign for each parameter. And we can find the W times X for each of these for each of these data points using these 4 features. And so we see here for all the class -1 data points, we get W times X to be less than -1. That's good. And for this one, we get -1 as expected, and this we get +1 as expected. And all the class 1 data points, we get the values actually greater than 0. That's actually good enough. We get actually greater than 1 for all of them, other than this one. It's like this one. So this is more like an outlier, we can say. Among all these records, this is like an outlier, but it's still greater than 0. So we are predicting correctly. But I would say this is relatively more closer to the other class. So we can check if logistic regression is able to find that out for us. So this one, it's not clear with logistic regression whether this record is an outlier, because it's just greater than 0. Okay, but support vector machine is telling us that this is in between 0 and 1. So that means it's greater than 0, so it belongs to this class for sure. But it's relatively more closer compared to other class 1 data points. It's more closer to the class -1 data points as well. Okay, like this one. So, like this one, we got 1 because we used it as a support vector, and it's more closer to the decision boundary. And this one is probably also closer to the decision boundary. That's what we can infer from these numbers. So if you're testing, fine, let's use this as a test case and get the normalized version of x1, x2, x3, and x4 using the corresponding mean and standard deviation. So substitute along with the bias one in w times x, we get -0.8522, and that's less than 0. So if w times x is less than 0, that belongs to class -1. Okay. So if you look at the numbers, it's 5431. So you look at the raw data. 5431. That doesn't really fit among any of this, but that's a good thing. So we are able to clearly pick up something as a test case, as it doesn't really resemble any of the training data points, and still you're able to predict the class for that. Okay. Now it's not less than -1 though. We got like -0.8522. So it's kind of closer to the class 1 data points, but still less than 0 though. So we can say it belongs to class 1. It's class -1. Okay. So that's this. So I have probably okay. So this is another example of a kernel trick which I do want to show. So we'll look at this after a break.